So now that you know how to determine the sequence of little proteins like meganin, your next job then is to figure out how to make something like meganin, because in reality, once you discover a new compound like meganin, you do not want to have to keep sacrificing the frogs to get that compound. So the whole point of determining what the structure is, so that next stage is to be able to synthesize the compound of interest in mega quantities, so you could use it as drugs. So this is what we're going to cover in this lecture, is how to synthesize peptides. And as you'll see pretty soon, this is not a trivial exercise. So as I mean, all these steps that you see in the sheet are just to make dipeptide. So let me just talk about why this is so difficult. So let's say you have two amino acids, glycine and alanine, and you throw that in the pot to make the amide between these two amino acids. And let's say you really want the glycine and alanine in that order. But what happens if you throw the two amino acids into a reaction flask? Problem is, each of the amino acids have two functional groups, right? The amino group on the left side and the carboxyl group on the right side. Amino group of alanine and carboxyl group on the right side. So even if I want the amide bond formed between the carboxyl of glycine and amine of the alanine, that is actually just one of the four possibilities that it could form, right? You could have alanine with glycine dipeptide, but it could also react with itself. There's no nothing forcing it to react with another amino acid. So you could have glycine with a glycine, and you could have alanine with alanine, right? So there are four possible dipeptides if you just react the way it is, right? So, and this becomes even worse if you have three different amino acids. You have 9 possible tripeptide. And if you have 10 different amino acids and you're making a decapeptide, then believe it or not, you have 4 trillion possible decapeptides. So you see the problem. You can't just throw in amino acid and hope that you get the protein that you want. It would be a 1 in million trillion chance that you will get that. So if you wanted to make meganin 1 or 2 that is over 20 amino acids long, and you want those specific sequence, you're going to have to come up with a better strategy than just throw it in and hope for the amide bond that you want. Okay, so the strategy for making peptides is that you need to use protecting groups to accomplish this. All right, so so you have an amino acid and you have the amino group and the carboxyl group, and then you have another amino acid, let's say we'll draw with the triangle with NH2 and carboxylic acid. So you have all these things. So instead of taking chance, what you do is, let's say you want the amino of this amino acid to stay intact and not react, then you put a protecting group on there. Protecting means like this amino group will not react, but it's because it won't be nucleophilic, but it will stay in this case. And when you're done, after all your amide bonds been made, then you cleave it off. All right. And if you want the carboxyl group, to not react, and you put a protecting group here as well. And then what happens is then these two are the only carboxyl, only amine group left. So therefore then you should be able to make an amide bond in between them, right? So what I've done here is go through that strategy step at a time. It's a little bit laborious, but you'll see the strategy in a minute once we go through them, right? So the first step in the strategy is that you have to protect the amino group. The N-terminal amino acid. All right, so in this case, we're gonna do a dipeptide synthesis of alanine with leucine. So obviously then I want the alanine N to have a protecting group. So that's what we're trying to accomplish. And these are the possible protecting groups. And that's just 3 of them inside the box. These are the most commonly used one, and these are the abbreviations for it. This right here, the abbreviation for that is FMOC. You'll see the chemistry of these in a bit. But what I've done for each of the step is the first equation is the general equation. So this alanine right here is going to have a protecting group attached to the nitrogen, and the specific reaction is shown underneath here. So here's my alanine with the, sorry, this is kind of faded, alanine with the methyl group here. And then what you're reacting here, this is the protecting group. And the specific protecting group that is used in this example is the benzyl chloroformate, okay? But all these react the same way, and this is a review of the acid family chemistry that you learned in Unit 3. This is an acid chloride, and you have a nucleophilic site, amine. You know that they exist as a salt, so that's why you need the base to pull off the extra proton to make the amine. So once it's nucleophilic in an amine, once it's an amine by deprotonating the proton, the extra proton on the ammonium ion, then it's ready to go and attack here at the electrophilic center. The double bond O breaks and then becomes O minus. O minus comes back down. Here's a good leaving group, makes it leave. So it's an acyl substitution reaction. And so notice this is the alanine, and then this is the protecting group. And what you've made is a new functional group that you haven't seen yet. Is basically an O double bonded and then N. So it's neither an amide nor an ester. It's a combo of the two. And these are called carbamates. And this functional group is often used as a protecting group for amine because it is not an amine, not an amide. And why is that important? It's important because the peptide bonds that you're going to form at this end is going to be an amide, so you want to be able to differentiate this bond from the amide bond, so you're able to cleave this off in preference to the amide bond later on, right? So it turns out the carbamates are easy to put on, as you see here with the acid chloride, and then they're easy to take off. And we don't want it to be so easily to take off so that it automatically comes off, you know, without trying to. So you want to have a protecting group that is sort of in the middle where it doesn't come off immediately, but it takes a little bit of effort. But in this case, It comes off when you want it to, all right? And the NH2 in this carbamate, the nitrogen is no longer nucleophilic. All right, so that's good because we don't want that nitrogen to be able to go and react later on. So we're making sure that the protecting group is protecting the amine, right? So that's why the carbamates are the protecting group of choice, all right? The second step after you protect the amine is to activate the COOH group. Now this step is not in your textbook really as a separated step. What your book does is they protect the amine, they protect the carboxylic acid, and then they react it together. And that strategy works if you're just making dipeptide, but I'm giving you a strategy where you can make as long of a protein as you want. So what you do is, because the carboxyl group of alanine is not a good leaving group when a nucleophile comes and attacks, we want to make it, what do I mean by activate, is we want to make it into this carbon. So this that we are putting on is a good leaving group. So the functional group that we are making is we're going from the carboxylic acid to this functional group, which is what? Anhydride. And we know from Unit 3 that anhydride is a lot more reactive in terms of being able to serve as a good leaving group over here. So that's what we're doing here. This is a specific reaction to activate the carboxyl group. So here's a protected alanine, and then we're using this reagent to make it into an anhydride, right? So now, and the other reagent that is used often to activate carboxyl group is DCC, which stands for dicyclohexacarbodiimide. This is used often, and its derivative, which is isopropylcarbodiimide, they are both used, and it has this structure, DCC. But anyway, this and the diisopropyl, so instead of a cyclohexyl, the isopropyl group, they work the same way. They're basically reacting at the oxygen of the carboxylic acid, and it's forming a good leaving group by this oxygen reacting at this carbon, and then the whole thing serves as a good leaving group. All right, so what you just want to remember for these reagents, DCC, diisopropyl, diisopropylcarbodiimide, those are all activating agents. All right. So I'll go over from the next step in the following lecture.